Okay, so the last subject that we're going to be looking at here in chapter 12 is going to be revisiting those normal and the tangential components of the motion that we see, on the kinetic side or the dynamic side of our motion, if you would. So if we look at the equations for motion, we know that we have some of the forces is going to be equal to the mass times the acceleration. Now, this acceleration, if it is going around a curve, okay, it will have those tangential and normal components, just like we saw when we were looking at just pure motion. Okay, now we're looking at in terms of the mass is moving along, so it is also going to have those tangential and normal components. Now, as we look here, we would set it up then where we would sum the forces instead of along an X or a Y axis, we are going in the direction of the tangential force. Okay, so that's what you see here on the left-hand side. The force is tangential. It is going to be along or perpendicular to the radius of rotation in the direction of the acceleration. Okay, so over on the right-hand side, when we set that equal to the other side of the equation, now the mass times the tangential component of the acceleration is over here. Okay. Then on the normal portion, our force normal is going to be acting just like it did for on the motion side. It's the force that's pulling in towards that center of rotation, causing that acceleration. And now we have that normal force again going from the element or the object pointing towards that center of rotation. So over on the right-hand side, when we look at the mass times the acceleration, now it's going to be the normal component times the mass of our object. Okay. Now, to calculate the values for the tangential and the normal components, it's going to be those same equations that we looked at earlier at the end of chapter 12. Okay, so before we go into our sample 12, our sample problem 12.6, let's take a peek at what you may have or what you might be adding to your equation sheet for what we've been looking at here in chapter 12. Okay. So at the top here, you're going to notice that Newton's second law says that force is equal to mass times acceleration. So if there's an external force acting on something and it's not zero, that means it's moving and it's accelerating because there is a net force. Then the sum of the forces is going to equal, if you would, the sum of the mass times the acceleration of that object. Now, if we are along whatever axis we are, then it's going to be the acceleration along that axis. So for some of the forces in the X, then it's going to be the mass times the acceleration in the X direction. If it's the Y, it's going to be the mass times the acceleration in the Y. And if it's along the Z axis, it's going to be the mass times the acceleration along that Z axis. This is linear motion. Okay. Now, rotational motion, like we had just looked at in this very last section, that is going to be equal to the force, the sum of the forces along the tangential axis or direction and the normal axis or direction. And that's going to be set equal to then the mass times the acceleration tangential and the mass times the acceleration normal. All right. Now, to calculate those individually, it's the same equation, tangential and normal, that we saw at the end of chapter 11. Okay. So the tangential component is going to be that change in velocity, final minus initial, divided by how much time it takes to change it. And again, its direction is going to be perpendicular to the radius in the direction of acceleration. Remember, that's different than the direction of motion. If we're speeding up, accelerating, it's in the same direction as motion. If we're slowing down, it's going to be opposite the direction of motion. The normal component, again, this is a repeat from the end of chapter 11. This is going to be the velocity squared divided by the radius of the curve or the distance from the center of rotation. This is phi, or sometimes referred to as r, lowercase r. The normal acceleration component is always going to point from the object to the center of rotation. And then I've got that little familiar diagram over here. Using those two components of acceleration, which are 90 degrees to one another, so tangential, normal, we can find the total or resultant acceleration by taking that Pythagorean theorem's form, where it would be the square root of the tangential squared plus the normal squared. And then the last thing I have added here, which we had experienced in the previous problem, is friction force. Just the definition of that. Friction force is equal to our coefficient of friction times the normal force. So just having that reference there. Now, additionally on my sheet, I've started to add what the final units are for different types of elements. So for instance, for mass, if I'm in the metric units, it's kilograms. If I'm English units, it's a slug, right? For force, I'm going to be in newtons or pounds, and a newton expanded is a kilogram meter per second squared. All right. I know I'm not requiring you to put units through the problems, but when you're identifying accelerations or velocities or forces, you need to have the correct units on your final answers. So it's always good to know these. And maybe you don't need to. Maybe you're like, I got the units, Kelly. I don't need to write these on my equation sheet. I know I'm like this. That's okay. Then don't worry about it. Weight, we calculate weight by taking mass times gravity. So the units for weight are the same units for force, so newtons and pounds. Velocity is going to be meters per second or feet per second. Phi, which is that radius, that's a distance, so that's going to be meters or feet. Acceleration and gravity is going to be meters per second squared or feet per second squared, with metric gravity 9.81 meters per second squared and English 32.2 feet per second squared. And then L, this is momentum. Chapter 16, we're going to have momentum. So we haven't covered that one yet, but that's kilogram meters per second squared. Okay. Now, again, this is my equation sheet, the things that I found to be helpful. All right. Yours can look completely different, and you can have less on it, you can have more on it, whatever you feel you need, but you have to have some sort of an equation sheet that kind of organizes our thoughts and equations from this module, okay? We will have additional ones pop in because we are going to be also covering chapter 16, okay? So I'll be adding to my sheet as well. All right, so just wanted to share that with you, and I can bring it out again if anybody needs it, during our break. But that just kind of helps to bring together the elements that we've been looking at here in module 6. Or I'm sorry, module 6, module 2, chapter 12. Where did I get 6? Oh, maybe from this. So let's take a peek at sample problem 12.6. So sample problem 12.6, we have a bob, okay? So it's really just a string with a ball on the end of it, and that's going to be able to kind of rotate or kind of oscillate back and forth here. The bob is on a 2-meter pendulum, describes an arc of a circle on a vertical plane. If the tension in the cord is 2.5 times the weight of the bob, in the position, or I'm sorry, the weight of the bob for the position shown, find the velocity and the acceleration of the bob in that position. So we want to find velocity and acceleration of the bob in this position. Okay, so let's go underneath. I do have sample problem 12.6. This is on page 737. Okay, so the first thing that we're going to do is we'll kind of identify our problem and our givens and what we need to find. So this is Sample problem 12.6. This is on page 737. Okay. The givens, okay. The tension in that cable is going to be equal to 2.5 times mg, or the weight of the bob. And the weight of the bob is calculated using mass times gravity. And then we also know that the length of that cable is 2 meters. We want to find the velocity of that bob and the acceleration. Okay. Probably lowercase b on Bob, because it's not Bob, a person name. It's Bob, a thing. But well, we'll call him, I'm going to go like this. Bob. Acceleration and velocity of Bob. All right. All right. So now we've got to draw the diagrams. Okay. Now, so when I first approached this, not this time, but last year, I remember doing this because I was like, OMG. So I had seen what they had done here, and I thought, okay, it's going to be like an X and Y component bonanza, which it is, because it's, everything's at an angle here. So then everything has to have an X and a Y so we can add and subtract them together. It got to be kind of a nightmare. And when I looked at how the book did it, I'm like, oh, that makes a lot of sense. So what we're going to do is we're actually going to use the axis system in the orientation that it is here. Instead of calling it X and Y, we're going to call it tangential and normal. Okay. Makes it a lot easier. At least I think so. So what we're going to do here is we're going to show this all at an angle. So the first one, oopsie, I'm going to use my protractor because then I can kind of get 90-degree angles. It's not imperative that you do this, but it does kind of help to use a protractor here. Now, my convention then is going to be this. And it's this because we're going to have things going down and to the left. And instead of, then we can just call them positive. So this is going to be our convention, and our axis is going to be the normal axis and the tangential axis. And then this center right here is the center of the bob. Okay. Now, this side here, I'm going to have one on the left and one on the right. My first side here is going to be my sum of my forces. So these are the forces that are acting on the bob. So the first one that we have is going to be the tension in that cable pulling towards the center of rotation. So this is going to be tension, and we know that to be 2.5 times mass times gravity, or the weight, right? Now, we know that even though this is at an angle, the weight of that bob is going to go straight down towards the center of the earth, right? So that's going to be our weight, and that's going to be equal to mass times gravity. Okay. Now, if we show the components of that, if I extend my normal axis, I go here and I do my little construction lines up to my tangential axis, that means that I have a tangential component along that axis. So this is going to be mg tangential right there. Does that make sense? Okay. And then going down and to the right, I've got a normal component of my weight. So this is going to be mg normal right there. Okay. Now the angle that this is at, given in our problems, is 30 degrees. So right there is 30 degrees. Okay. So those are all the forces acting on the bob. The tension in that cable, and then the weight coming down with the two components along the N and the T axes. okay? Now this is going to be equal to, and we're going to do that very same thing where we're going to have our n-axis and our t-axis, our bob and the center. Now remember, this is the mass and the acceleration. So this is my t-axis, my n-axis. Remember, there's two components of the acceleration. It's tangential and normal. So I'm going to do the normal first. So this is going to be mass times the normal. Remember, the normal is always going to go from the object and point towards the center of center, in this case of rotation of our bob. So this is going to be mass times the normal acceleration component. And then the tangential is going to go in the direction of acceleration, and it is going down and to the left as described in the problem. So this is going to be mass times acceleration tangential. So we have two axes we're going to go along. We're going to go along first. You can pick whichever one. I'm going to do along the t-axis first, or the tangential axis first. So step one is going to be along the t-axis. Okay. We're going to have some of the forces along the t-axis is going to be equal to mass times the acceleration along the t-axis. So we're just looking here and here. Okay. So just looking along that t-axis, and remember, our convention says down and to the left is positive. On the left-hand side, we're going to say mg tangential is going to be equal to, also in the positive direction, m acceleration tangential. Now, mg tangential, this is a component of our weight. So that is going to be equal to, if this is the 30 degrees, if we go opposite, this length right here is an equivalent length. So that's the side opposite in terms of the hypotenuse. So the hypotenuse is m times g. So this is going to be sine of 30 times mg. Okay, so the tangential component is sine of 30 times mg. So we're putting it, if you would, in terms of the weight, which is mass times gravity. It's going to be equal to mass times acceleration tangential. Now, as we look here, do you see how mass is on both sides of the equation? They cancel out. And if you remember from physics, that like happens all the time, right? It's like mass is never a big deal, right? So when it cancels out, you're like, oh, that's nice. And what's kind of convenient is it didn't give us the mass in the problem, right? So, or we didn't have to solve for it. So mass cancels out here. So 0.5 is going to be the sine of 30 times 9.81 is going to be equal to the acceleration tangential. So 4.905 meters per second squared equals that tangential component. All right. So we're going to put a little cloud around there because we want to find acceleration. So this is one of the components of the acceleration. So we're not there yet, but we need the tangential. Now we need to go along the normal axis. So step number 2, I'm going to call it, is going to be along the normal axis. Okay. This is going to be sum of the forces, N equals mass times acceleration normal. So if we look up here, we're now looking along this axis and this axis. Okay. So on the left-hand side, the sum of the forces along the n-axis, we're going to have a positive 2.5 mg and a minus mg normal, right? Okay. So left-hand side is going to be 2.5 times mg minus mg normal is equal to, mass times acceleration normal. That's all in the positive direction. So M A N. Now, this quantity here, the normal component of the weight, M times G. So the normal component here, if we notice where our 30 is, this is the side adjacent. So that is the cosine, right, of 30 degrees times mass times gravity. So we're going to leave that 2.5 mg out here minus, cosine of 30 times mg. That's the normal component, is equal to mass times acceleration normal. Now, 30 cosine, the decimal equivalent is 0.866, right? Okay. So we're going to have 2.5 mg minus 0.866 mg is equal to MAN. So these two we can combine now, right? 2.5 minus 0.866. Okay. So that, right? Oh, I see what yeah, either way. It's two ways. I did it a little bit different on my piece of paper. So 2.5 minus 0.866. So this is going to be 1.634 mg is equal to mass times acceleration normal, right? Mass is on both sides again, right? So we can cancel out the m on either side. And we know that gravity is the 9.81, right? I've run out of room here. I gotta go to the other side. I'm going to continue on. So gravity is going to be 1.634 times 9.81 is equal to the normal component of acceleration. So if I take 1.634 times 9.81, oh God, I get 16.03 meters per second squared is the normal component of acceleration. Okay. So what we just calculated for was the normal and tangential components. So when we look over here, that's the normal and the tangential components. Okay. Now, they're asking us for acceleration. They didn't ask for normal. They didn't ask for tangential. But to get there, we need both of those. And then we're going to use them in that Pythagorean theorem form. So this is going to be step number 3. Our acceleration is going to be equal to the square root of the tangential component of acceleration squared plus the normal. Okay, so go ahead and fill that in with the numbers that we just got and make sure you can get an acceleration of 16.8 meters per second squared. Show the numbers in there, okay? I'll let you kind of fill that in. If you've already completed it, did you get 16.8? Jacob did. Yeah, good. Good, good, good. Pull the chat box out. Now, they wanted us to find the acceleration, so we just did, but now we have to find the velocity, okay? The velocity, so that is going to be, if we look at our bob, since the tangential component's going in this direction and it's accelerating, it said in the problem, that means that we have a velocity in this direction as well. Okay, that's going to be our velocity of our bob. Now, how are we going to calculate that velocity? I look back at my equation sheet and I'm kind of in this zone right here. See this one right here? If I take the normal component of the acceleration, it's equal to the velocity squared divided by that radius, okay? Why can't I use the tangential? Can't I use the tangential? I'm really not given two values, right? I also am not given a time at which this is happening. So I couldn't use the tangential, all right? I have to use the normal because they did give me the length of the cable holding that bob. Okay. So we're going to use that normal component. So step number 4, normal is equal to the velocity squared divided by the radius. So I know that my normal is the 16.03. My velocity is here. And then I also know that my cable is 2 meters long. So rearranging this, I'm going to say velocity is equal to the square root of my normal component times the what is that called? The radius of the curve. And in this case, the length of our cable. So this is going to be equal to the square root of 16.03 times 2 meters. Let me put the meters in. You should get a velocity of 5.66 meters per second. All right. You guys get that same number? Awesome. Good. Good, good, good. Okay. Kind of a fun little problem. Yeah, the key here when you set it up, oopsie, let's look at the one that I made here. It's easier without the lines. It's a lot easier that when we set our axis system along the lines that we have here. If you could, I mean, I've had students that put it through here. They're like, no, I want to try the X and the Y. You can, but it's really, there's a lot of numbers to deal with when you do that. This really simplifies it when you push it right along there. And then adding, in this case, because it isn't an X or a Y traditional, I thought, well, then let's put the positive to the left. Why not? Right? So there's fewer negatives to deal with, which is always positive. See what I did there? Yeah. Danny did. No one else did. All right. So that's problem 12.6. Now, we have done all 3 of the problems, sample problems that I wanted to in chapter 12 here, which is the first half of module 2. Let's look at our homework assignment. Okay. Let's look at our homework assignment. This away. So I'm going to go over to the well, let's first look at the practice problems from module 2. We have done the first 3 here, so we're halfway done if you would, okay? Which puts us in good shape for the next time that we get together. Let's look at the application problems because now you will be able to do some of these. In the end of chapter or in the chapter problems that they had, I just didn't like them. I was like, and then the problems that I felt were the ones that I did for the sample problems didn't really lead very well into the ones that they had. So I decided to make up my own based on the sample problems. So the first 3 problems here, I'm calling them application 1, application 2, and application 3 are all from this chapter 12. Okay, so there aren't any specific chapter 12 ones. It's just going to be these 3 problems. And how I have it set up is the first application, it says using sample problem 12.1, which was the first sample we did here in chapter 12. It's on page 731. I want you to find the acceleration of the block, noting the following changes. So similar problem, but this time you're given the P, okay? that you're going to be pushing the block with. So let's take a peek at that sample problem, kind of reminding us what that one looked like. So let's go underneath. Okay. So problem 12.1 on page 731, this is looking at that block. Now, in this case, we had to solve for P. I'm giving you, what is that value? So in this problem, P is 250 pounds. The weight of our block is 150. So it went from 200 to 150. And then the angle is 40 degrees instead of 30. Okay. And what I want you, and then I also am telling you that the coefficient of kinetic friction is 0.33. So it's a little bit different than the one that's here. And what you're going to do is if we go back over here, you want to find the acceleration of the block under these conditions. And then your final answer, you should get an acceleration of 19.1 feet per second squared. Okay. So use that same problem. It is a little different. You're solving for a different variable. In the problem, sample 12.1, you were solving for P, and this one you're solving for the acceleration. Okay. So that's your first application. The second application problem that you have is going to be using problem 12.3. Okay. And in this case, you're just going to redo the same problem, noting the following changes. Block A is going to have a mass of 225 kilograms. Block B is going to be 485 kilograms. Otherwise, everything else is the same. Okay. And that one is the two blocks with the pulley. So go through the same process, different masses. Okay. And then find the accelerations of each. Okay, so that's the second application problem. The third application problem is you're going to use that last problem that we looked at, sample problem 12.6, which is the bob, okay? And you want to find the total acceleration of the bob to maintain a velocity of 8 meters per second, noting the following changes. So in this case, the length of the cord or the cable is going to be 4 meters. The angle is going to go to 45 degrees instead of 30. So if we look back here on the on the illustration, it was 30 degrees here. I want you to change that to, did I say 40? 45, sorry, 45 degrees instead of the 30. And then the tension in the bob cord is going to be 2 times the weight. The original problem, the original example was 2.5. So you're going to now find the acceleration to maintain an 8 meters per second. Okay? So good. So that one's just slightly different, okay, than the original problem. So that would be what you're ready to start for or start doing if you wanted to work on the application problems for module 2. The rest, you'll notice that there's 3 from chapter 16, and the next time we get together, we will make sure that we cover what you need to work on those. Any questions at this time? Okay. So then that means that I am going to stop the recording.